Good evening, everybody. My name is Matheus, and I'll present problem 15, continuing with honey. So the problem asks us to construct a device that continuously steer a cup of tea with a teaspoon of honey at the bottom, and then to discover when it will be uniformly distributed and dissolved, and also to determine the homogeneity of the system, and to make variations such as adding sugars and honey or a slice of lemon, for example. So I'll start with an introduction, then make some experiments, and then make a conclusion. So about the theory. In theory, we'll talk about the transport processes. Diffusion in fluids, they happen from high to low concentrations whenever we have no external interference. And they also take a long time to happen, for example. So if we add a spoon of honey at without external interference, they will not be uniformly dissolved after a long time, for example. So how do we manage to do it? We constructed a magnetic stirrer that will work somehow like that. So talking about the magnetic stirrer, these are the fluid flow lanes, the application of the divergence, for example. And the magnetic stirrer, it creates a vortex within a vessel because we have a rotating magnet at the bottom, and the fluid follows a diffusion pattern that will happen like this. And we chose it because it is energetically efficient and has a low sound dissipation and low heat dissipation, for example. So, about the important parameters considering this magnetic stirrer, we consider the fluid viscosity that decreases with higher temperatures and also that increases with higher concentrations. We also consider the magnetic coupling between the magnets at the bottom and inside the cup, the vessel. Also the rotation per minute of these magnets, and also the geometry of the cup, which we consider the best one as the one we had when we had a circular bottom. So about the homogeneity criteria, we use light scattering theory. Whenever we have a laser beam passing through an empty vessel, for example, we'll observe that the same intensity of light that reaches the other side after it passes a distance d will be the same. When we add honey, for example, we'll see that this intensity of light will change from I0 to I alpha. When we start mixing the solution, you can see that the intensity changes and will become much smaller than this I alpha. It will be an I beta, for example. This is the top view that was rotating there. And after the process, the intensity returns to this to its value, I alpha again. So we propose this method considering the light scattering, consider this equation for this light scattering that takes into account as the particle density, the sigma is the cross section, and considering the distance between the two walls of the vessel as being z, and we reach this exponential z. So we'll talk now about our experiments. This is our experimental setup. This is only a draw. We'll see an image later, but the light of the laser beam will pass through three polarizers. It will reach the vessel that will have the honey and the tea, and etc. Here we can see the motor that will be rotating powered by an AA battery. And then at the other side we'll have a receptor that will capture the intensity of light and provide us all the experimental data we want to try to work with. And this is an image of our experimental setup. As you can see here, the magnetic stirrer, we can see the laser beam, the polarizers, etc. And also, we consider experimentally this refraction angle here because whenever we have change in the medium, we consider this refraction angle by the light of the laser beam also. And this was determined experimentally for when we used it. About some optical and mechanical conditions to our magnetic stirrer, we considered, for example, using the motor clockwise or counterclockwise. You can see that the efficiency is almost the same. And also, we considered the properties magnetic properties of it whenever we didn't have the contact with the magnetic bar inside and without it. And we can see that the RPM is completely affected by this effect of this addition of this new bar. And this is a typical experimental time trace. As you can see here, in 1, we have the initial phase. In 2, we have the addition of honey. As I said, we have a decrease in this intensity of light. At 3, the process of steering, it starts, and then in 4, it reaches the stabilization plateau. And it's important to say also that before we make this, we calibrated the sensor to measure about 80% in arbitrary scale of intensity of light. So this is a typical time lapse. As you can see here, when it starts, and when it reaches the stabilization plateau after a while, which is quite similar to the one found by the other team. So I'll make 4 experiments concerning the concentration of honey, temperature, comparing sugar and honey, and also the addition to the lemon, the addition of lemon. As here we can observe the graphs for the concentration of honey, considering half teaspoon of honey and 1 spoon and 1.5 and 2 spoons of honey at a temperature of 30 degrees Celsius. And we can see here that the more honey we get, the more honey we have inside the vessel, we'll have more time for stabilization. And there used to be another slide here, eraser, but it showed the time. Okay, it happens. So the result about concentration, we use the fit function of an exponential decay, and we obtain this graphs here with an R-squared of 4.9. And considering the experimental data we obtained and using the light scattering function, we were able to combine them both into this new equation, remember the light scattering that I said before, where n can be approximated to the concentration of honey. And here we can see a linear relation between the concentration and the logarithm between the intensity that reaches the vessel and that goes out of the vessel after the steering time, and which is a great fit, and we were very happy with it. Now, considering the results in temperature, using 5 milliliters of honey and 250 milliliters of tea, we can see that with higher temperatures, there's a less time for stabilization. There would be another table here too. This is the table I was talking about. I thought I had forgotten, but it was actually this table, as you can see here. There's a difference in time between all the temperatures we measured. Now comparing both sugar and honey, as you can see here, they establish themselves with 2 different plateaus. And here we consider this because we consider honey as having a higher density and sugar having a higher molecular separation. And this intensity of light is directly refracted by it, because you can see there's a less intensity of light to honey and more intensity reaching the other side from sugar. This is why you get these 2 differences in plateaus. And also the time of stabilization happens really fast, and these are some dollars for it. So in results comparing sugar and honey, we have an almost time, the same time t for stabilization. There's a difference in plateau due to these 2 things I mentioned before. So results adding lemon to the tea, as you can see here the times. We also did not observe many differences between 2 of them. As you can see, and now comparing and analyzing this graph here, and talking about the same things we had before. Honey with lemon reaches a lower plateau, and we considered biochemistry in this analysis, for example, due to the intermolecular action from the lemon as an acid breaking the sugar complexes in honey, and sugar reaching a higher plateau because of the smaller sugar particles. So in conclusion, to have a less time for stabilization, we can consider the parameters such as temperature and concentration. And we consider that adding sugar to this tea at high temperatures will have a similar time with no significant differences. Adding lemon to the tea also will provide us no significant difference in time for stabilization too. This is our geography, and thank you.